All right, we're live.
Okay, good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our SETI Live. So today we are going to talk about habitable planets and how many of them we can find in our galaxy in the Milky Way. And for this, I invited my colleague, Jeff Coughlin. Hi, Jeff.
Hey, hi Frank, how's it going?
Good. Where are you located right now?
I'm currently right near Seattle, Washington, and amazingly, it's not raining yet.
Okay, so I'm in San Francisco in California. So we're gonna have a very interesting conversation about a new paper that you co-authors together with 100 co-authors to talk about the number of exoplanets in our galaxy. So before we start, I just would like to remind you, our viewers, that you can send us questions directly on our YouTube feed. Click on the chat button on the right. We will take some time to answer to your questions, of course. Tell us where you are watching us, listening us from this planet, but also from another planet, maybe. We never know. Internet can go there. And also, don't hesitate to tell us what you like or dislike of this SETI Live, of course. So, Jeff, very good paper last week. It was published on Thursday, where basically you announced and your team announced that there is, in the 100 billion potential planets in our galaxy, there is 300 million exactly habitable planets in our Milky Way. Is that correct? Is that exactly the number, or you counted
Not quite right, yeah. So it's all statistics, and statistics means nothing is 100% is accurate. But what we found is that we know that there's at least 300 million planets that are likely the size, about between half the size of Earth and 1.5 size the tons of Earth, so that they're probably rocky, and that they're in the right distance from their parent star, so they're in the habitable zone, so they could have liquid water on their surface. So at least 300 million planets like that, and likely more, that are in our galaxy alone.
That's a gigantic number. I mean, that's such a big number that I have even a hard time to envision what is 300 million. So you basically use the Kepler catalog to derive this number. Maybe you can tell us first what is the Kepler mission, because some people may still not know that, and then tell us exactly what you did with these observations from the Space Telescope.
Cool. Yeah, so Kepler, for folks who haven't heard about it, is a telescope in space that was launched back in 2009. I can't believe it's over a decade ago now. I remember watching it launch in grad school and having funding tied to it and going, please don't blow up, please make it. So it had a really dedicated mission, which was to hunt for exoplanets. So at that time, we knew of a couple hundred exoplanets that have been found in the 20 years prior, but they're only about the size of Jupiter. Or maybe a little smaller. Kepler was the first time that we could actually detect planets the size of Earth, or even smaller. And so Kepler hunted for about 4 years in its prime mission and did another 4 years in extended mission. And over that time, it discovered thousands of exoplanets. And that was, that was over the 8 years. What took us a couple years after was working through all those detections and getting the statistics right so that we could really accurately determine, again, how common planets, at least the size of Earth and the right distance from the host star, are out there. Yes. And that's what this paper is really the culmination of.
Yeah, let's give some numbers here. So Kepler stayed at the same field of view for the first 4 years,
That's right.
which is not too far away from the center of the Milky Way in the constellation of Cygnus, if I remember properly.
That's right, right towards Cygnus.
And in this patch of the sky, which is 10 times the size of the moon. I don't remember, frankly. I'm mixing up with tests now. You observe 150,000 stars. Okay.
That's right, yeah.
And those 150,000 stars, you basically measure the brightness of them continuously for 4 years. And the goal is to observe not the planet directly, but the shadow of the planet while the planet is passing between us and its host star. So
that's right.
You see a small attenuation of the brightness of the star.
Yeah, and so to find a planet like Earth, you need to wait an entire year and stare at that same star for an entire year to see it pass in front once. And then to be sure it's not an artifact or something else, you need to wait another year to see it a second time and be really sure. You kind of want at least 3 events. So when you see that 3 events spaced all equally, you're pretty sure, hey, I think that's a real planet.
Yeah.
So take some time.
People often ask, but how come we have to send a Kepler mission and wait 2009 to get that? Well, because the attenuation of light is super small. I mean, it's the order of part per million. So especially for a very small exoplanet like an Earth-like exoplanet, an Earth-size exoplanet, it's super small. So what you don't see something obvious. You see something like a very small attenuation that lasts for what typically?
About 12 hours for a planet like Earth, but that's only 12 hours out of 365 days that you see this tiny drop in light that's like a firefly passing in front of a spotlight. So it's an extreme technical challenge.
It's always amazing to me when we describe this problem, how we managed to do that, and from space using a space telescope. So Kepler discovered I'll have the number on the paper, 434 planet candidates, and 2,300 of them got confirmed as exoplanets. So that's a lot. That's basically half the exoplanets we know so far have been discovered by the Kepler mission. That's a beautiful result.
Yeah.
Okay, but now, before we go through the details of what exactly this mission brought to you, let me say that we have a lot of viewers from various places. So let me guess: Ireland, Atlanta, Georgia, Atlanta, Virginia. We have people from Ohio, Indiana, Australia, Brazil, Kentucky, Troy in France, Zeta Reticuli, so that's a joke probably, Redville, Columbia, Florence, Massachusetts, Canada, Minneapolis, Amsterdam, California, Michalovce in Slovakia, hello, and Chicago, Washington State, Alger, Fremont, California, very close to us, and in Italy. So we have people from various continents here, already 3 or 4 continents. So thank you for following us, and don't forget, you can ask questions, and Jeff will take the time to answer to all you complex questions. So we talk about Kepler discovery. So now let's go through the interesting part of the paper, which is the calculation of the parameter called Eta Earth. Is that the way you say it? Because
that's the common term and the community uses.
So what is Eta Earth?
So Eta Earth is basically what is the frequency of planets like Earth around other stars, and specifically around stars kind of similar to the sun. In terms of the search for life, we're here on this planet. This is life as we know it. So let's see what other planets similar to Earth are out there. So if Eta Earth is 1, that means every single star out there has a planet like Earth. If Eta Earth is 0.01, only 1% do.
And that's a parameter was defined in the Drake equation. That just mentioned, because the Drake equation is kind of the foundation of the SETI Institute's research group. Each of us at the SETI Institute work in specific area, and our goal is to kind of estimate one of these parameters of the Drake equation. So it could be Eta Earth, like it could be the duration of a technological civilization, the L, like it could be the rate of formation of stars in the galaxy. I mean, there is multiple parameters in this equation. So this paper is truly basically a measurement of Eta Earth from the Kepler last catalog data, DAR25. So is DAR25 the final catalog of Kepler, the Kepler mission?
Yeah, that was the final catalog, and that took a couple years to really put together after we stopped collecting data. Because again, we needed to make sure that it wasn't enough just to find the planets. I mean, that was really fun, and there were a lot of press releases and a lot of big discoveries on, oh, look at this planet, and oh, this is a really neat planet. But Kepler, the entire time, its mission was to do good, solid statistics. And so it took a couple of years to make sure that how we measure planets, we account for all the planets that we couldn't see, and we account for the things that look like planets but didn't turn out to actually be them. And that was the bulk of the work over the past several years.
Yeah, we often say in science, it's always easy to publish what you see, and it's very difficult to publish what you don't, and to do some statistical analysis to understand a negative result. So this paper is truly about publishing a negative result. I mean, you focus on you use the detected exoplanets to infer the the rate of detection, but ultimately most of the analysis is due to the non-detection of exoplanet, basically. So you say we are looking for exoplanet like Earth in orbit around star like the Sun. Can you clarify this? Can you give us some kind of the range of research you have?
Oh, sure. So stars come in a variety of sizes and temperatures. And for a planet to be habitable, there's some extreme limits where we think that might not be the case. So there's challenges if you're not around a star like the Sun. So if you're around a really low mass star, kind of like our neighbor Proxima Centauri, you could technically be in the habitable zone, but there's a lot of outstanding questions on how habitable it really is. One challenge is the planet may be tidally locked to the star, and what that means is that the same side of the planet faces the star all the time, and we're not sure how that may affect the atmosphere and the habitability. And another one is those types of stars have a lot of very energetic flares, and so it's possible those flares may periodically sterilize the surface of a planet. Not 100% very active area research, but for this study in particular, we really wanted to limit it to stars that were either only a little less massive than the Sun or a little more massive, where they behave like our own Sun. And we know life can be here since we're here, so life can probably be around those other similar stars.
So you voluntarily restrain the search for the stars which are identical to the Sun, because you know that the habitable zone is the order of a rotation of a period of 360 days, roughly. And also,
Yeah.
you want to find. It's so difficult already to find life that the idea is to restrain this search to life that could be like ours. So in orbit around stars that are identical to our stars with the same temperature and the same type of activity, basically.
That's right.
Because life could exist around M-type stars or around OAB stars, definitely, but it would be so different to our life that we may have a difficulty to find it, to identify it. And the goal here in this paper is to find Eta Earth for planets in orbit around stars like ours. So despite this limitation, you got this number of 300 million at least habitable planet in our galaxy.
Yeah, that number is really kind of it's a minimum number we're comfortable saying. That with high confidence, we know there's at least 300 million planets. Again, that's similar size of Earth and distance from their host star. But when you do the full statistics, that number could be as high as a couple tens of billions, or maybe even more than that. And as you said, that's just around sun-like stars. So if you're talking about any form of life in the universe, that's kind of a minimum. The chances are even greater.
So I want to clarify to people that are watching us here, because I see already some comments. When we talk about habitable, we're not saying inhabited. Okay, that's a very significant difference. Habitable means that the planets could have liquid water on the surface if it has the same pressure, atmospheric pressure, roughly than Earth. Is that correct?
Yeah, that's right. We're really just focusing on, there is nothing about this planet that rules out the presence that liquid water could exist on its surface. We don't know for sure if it has water or not, but we think it has a rocky surface where water could pool and in the right temperature where it's not going to freeze and it's not going to boil off. So if there was liquid water there, if there was water there, it should be liquid and be able to host life. But we don't know anything more than that.
People often ask why we are so obsessed with this liquid water in our search for life. I'm just going to mention that life on Earth appeared very quickly. 500 million years after the formation of Earth, we have indication of the presence of bacteriological life, because this bacteriological life developed in water, despite the fact that the planet was totally not hospitable. Earth at the time has a strong radiation, strong volcanic activity, impact of asteroid. There was already some kind of life in this liquid pond or liquid ocean. So that's the reason we are so focused on this search for liquid water, because we think that's an indispensable indispensable medium to find life, and life which could be identical to our. Okay, so so I noticed that you use the Kepler catalog that your group I mentioned, I don't know if I mentioned that you're the director of the Kepler Science Office. So you basically your group is the perfect group to do this kind of of work and data analysis. You released the AR25, which was the last catalog. But in the analysis, they use as well the Gaia data. Can you tell us a bit what is Gaia and what they use it for?
Yeah, that was a really nice result that happened to tie in with Kepler that I don't think was foreseen when Kepler necessarily first launched. So what Gaia did, Gaia was a European mission, and it measured the size and age and temperature and brightness of billions of stars in the galaxy, and it did it really precisely. So before Gaia, we knew kind of which stars we were looking at, but we said, oh, that star, that's kind of the same size as the sun, but plus or minus 10 or 20%. And when you don't know the size of the star really well, because you're measuring the planet size relative to the star, that means you don't know the planet size really well. So without knowing the star, we couldn't know exactly the size of the planet. Gaia came along, and now we know the size of these stars to only a couple percent, which is really precise. So that allowed us to measure the size of these planets much more precisely, and that allowed us to get better statistics and a more accurate answer. So it was a really nice synergy between the two space telescopes.
Yeah, I think it's incredible that we send a spacecraft, which is basically now mapping the galaxy and give us so many information about the distance of those stars and their location, their proper motion as well. I mean, a lot of scientific results going to be coming from Gaia, which are sometimes related to the search for life, the search for exoplanet as well. We will talk about this in the future, probably. So, so now we basically have a better understanding of Eta Earth, the famous parameters. In the introduction of the paper, you give some kind of estimate, which is 0.37 or 0.6, depending of the type of habitable zone you consider, right?
Right.
And then for this from this number, you take the number of stars in our galaxy, which is varied, but typically 100 million. Yeah. We know the fraction of those stars, which are FG case type, so sun-like, and they call them dwarf stars in the main sequence, if I remember properly. My class is in evolution of stars, and then you basically got this enormous number of 300 million. Can you tell us why you say it's at least?
Yeah. So again, going back to, we never know anything with 100% accuracy, but we know that it's, for all purposes, it's basically about half. We said, all right, about half of all sun-like stars have it, but we're really confident that it's like at least 20% and maybe as much as 80%, but the average is around half. So we said, even if you go with that lower end of, say, at least about 20%, and then you apply that to all the stars in the galaxy, that's at least 300 million. And so that's why I said it's at least 300 million, but really could be much higher.
All right, so we talk about the Drake equation. You mentioned that we are learning about life in our galaxy and the universe from this equation. Probably you know it by heart, right, this Drake equation. So where are we now? We are basically, you think we have solved the issue of Eta Earth, definitely?
I think it's basically as good as we need it for now. Before Kepler launched, we weren't sure if Earth was 1 in a billion or 1 in a million or 1 in 1,000. And now we're kind of saying it's 1 in 2, that it's around 50% of sun-like stars have an not Earth-like, but at least a planet the size of Earth at the right distance. So, I mean, that's huge. We were saying earlier, you know, how big is Eta Earth? That means the chances of another truly Earth-like planet being out there with oxygen and life are that much greater. So yeah, I think it's kind of time now, move on to the next step. As you said, there's a bunch of people at SETI doing different amazing things. And one of those is talking about the origins of life. How common is it for life to evolve and start? How does that happen? And so the next generation of space telescopes are going to start looking at some of these exoplanets and see what their atmosphere is made of. And so we'll start to find out how many planets out there have a nitrogen oxygen atmosphere like Earth. Do any of them have signatures of life called biosignatures that we can detect? And down the road, it's I think a couple decades out, it's not unusual to think there'll be a similar conversation like this, where somebody is saying, oh yeah, we now have thousands of biosignatures out there from the millions of planets we've looked at, and now we know the frequency of life, of basic life out there. That's really not that far off when you think about it, which is incredible.
That's totally blew my mind. I mean, I started astronomy in 1996 when we knew just one exoplanet. The Drake equation, we knew only the rate of formation of stars in our galaxy. And now we can say that 50% of the star, like the sun, have a terrestrial planet in orbit around them in the habitable zone. I mean, that's an amazing number. And I think I don't really yet grasp the reality of what's going on here. But if we had a spaceship, basically, and you mentioned that in the paper, you say that if we could fly 10 parsec around the sun, which is 30 light years, we will find 4 habitable rocky planets in orbit around stars. In average, I mean, there is a lot of worlds there that could be habitable, and maybe one of them it's very close to us. That's amazing.
Yeah, that's a big number. So 30 within 30 light years, our statistics say there should be about 4 planets, again, about the right size and distance from their star. And I mean, that's incredible. 30 light years on a cosmic scale that's right down the block, right? That's a couple houses down. That's really not that far in galactic terms. And I think it's neat. We're already seeing this. We've already found the closest Earth-sized planet to Earth that we'll ever find, because we know of one around Proxima Centauri b, and that's the closest star to the sun. And we know that has a near Earth-sized planet in its habitable zone. Now that's one of those really low mass M-dwarf stars that we're not sure how much the flaring hurts life and all that. So it's not quite sun-like, but it's still neat that we already know that one's literally the house next door. So yeah, we're saying that there could be around sun-like stars, several in the neighborhood.
Yeah, and if Proxima Centauri has 1 or 2 terrestrial planets, it's very likely that Alpha Centauri A and B, which are sun-like stars, could have as well the terrestrial exoplanets. And there is missions to basically look for those terrestrial exoplanets around Alpha Centauri A and B, because they're so close to us. Yeah. It will be not easy, but quite possible with the current technology to find them. What you just need is the focus of a mission or an instrument on the very large telescope, extremely large telescope, to be able to see this Earth-like exoplanet. And that's going to arrive soon. I'm very optimistic, and I think in 10 to 15 years, there's
been great proposals out there to really do it for Alpha Centauri for cheap, because you're right, it's such a uniquely close and bright system. It's not that hard.
So let's compare about this. I mean, I heard critics about this paper, and one of them was that, in fact, Kepler has been looking at one area of the galaxy, one patch of the sky, with 150,000 stars. So tell us a bit about this kind of conversation. What exactly people are thinking about when they say that?
Yeah, so the field of view of Kepler is only about 0.25% of the entire sky. So it's a little tiny slice. And so that field of view was really chosen to be a representative good part of the galaxy to sample. It wasn't too close to the center of the galaxy. It wasn't too far away. It was kind of along a couple galactic arms. So we think we're getting a good representative sample. And with an election tomorrow, it's kind of like polling, which has been in the news a bunch. If you sample the right 1,000 people and you really get a good sample and you take all the factors into account, that's still, your statistics are good. You don't need to look at everything. And so that's what we think we did with Kepler. We chose the right sample of stars. We controlled all the variables. We studied it really well, and we think our sample's right. And what's interesting now is you have other missions. You had K2, which was the second part of Kepler that looked at a bunch of fields around the galaxy. You have the TESS mission, which is surveying the entire sky to find exoplanets. And what's neat is we're just starting to get some initial results of statistics from those missions. And so far, those estimates of how common planets are in general seem to line right up with the Kepler field. So although the galaxy may not be entirely the same everywhere, it seems that the rate of planets roughly does seem to be the same throughout the galaxy. So the Kepler results so far seem that you can apply them to the entire galaxy.
Yeah. And another critics I heard from colleagues is the fact that Aerobars are gigantic on those numbers. I mean, they're not that big, but they are big.
They're
And the reason for this is basically the lack of detections. I mean, Kepler did not observe that many Earth-size exoplanets in orbit around G/K type stars. Maybe we should say why first, and then maybe discuss about this.
Yeah, the why is because it's really, really difficult. Kepler was really pushing all the technological boundaries when it launched to be able to detect planets this small and this far from their star. Yeah, we kind of got right to the edge. So we didn't directly detect lots of planets that were exactly the same size of Earth around G-type, around the stars like our sun. But we did detect lots of planets, and we detected them as small as Earth and somewhat close. So we got really close to detecting those true Earth analogs. But we got so many that you can see the trends. You can see that as planet sizes get smaller, planets get more and more numerous, more frequent. And that as you go far away from the host star, the number of planets doesn't seem to drop off too much. So we had enough other numbers where all we had to do was just extrapolate a little bit, and you can get to that true Earth analog kind of parameter space that a statistics covers. So yeah, the Aerobars, I'd love them to be smaller. You need to launch another Kepler or another next generation mission to get them smaller, but they're still good to go forward with.
Good, thank you for this answer. This very clear answer, in fact. So we're having questions here. I'm going to take some questions. One from Glenn. What elements does SETI Institute consider habitable? Are you searching for anything that might not support Earth-like, but something else that might be possible?
Yeah, and so yeah, kind of you said before, we're searching for what we know, and that's liquid water. Everywhere on Earth where we have liquid water, we find life. And so far, places that have absolutely no liquid water, we don't really find life. So that's been the main constraint. So that's what Kepler focused on, was those conditions of having liquid water. But yeah, who knows? I know people at SETI are studying other possible forms of life, whether it's silicon-based, whether you can have life in methane lakes like there is on Titan. Is definitely an outstanding question. So yeah, I like thinking that our answers so far are a bare minimum, and there could be other habitable worlds out there.
So a question that we already have answered, but let me just make sure we answer that again. Do we know the percentages for water on those exoplanets? Do we know how wet they will be or not?
So for the Kepler planets, we don't, right? So the planets we studied, we don't know for sure whether they have water or not. We're just saying they have the right conditions where water would be liquid if it was there. What is neat, though, is that we're starting to get more and more other planets that have been studied where we can detect what's in their atmosphere. So a lot of Jupiter and Neptune-sized planets, we've actually found methane and carbon dioxide and water and nitrogen and all these other basic, building blocks of life. We know are present in other planets and their atmospheres. We just haven't been able to get down to the Earth-sized, really small, difficult to study planets yet. But that's hopefully what the next generation will do, is it'll study those Earth-sized planets and tell us if indeed they have water or not.
This is a good transition for the next questions. Will the SETI Institute scientists have access to the James Webb Space Telescope if one day get off this planet? And what kind of information could we get about those exoplanets from this fantastic new space telescope?
Yeah, I know there's SETI team members that are working with James Webb data and waiting on that telescope to launch. And James Webb will be fantastic because it'll be able to probe those smaller planets and, again, study their atmosphere, find out what they're made of. And then eventually all the James Webb will be data. So all the data will be public, so everybody in the world can study that. But yeah, James Webb and the telescopes to follow it's going to be a flood of information about the chemistry on other planets.
So we talk about SETI transiting exoplanets and future instrument to study transiting exoplanets in one of our SETI Live last month. We talk about Plateau, for instance, which is going to be a very interesting mission from European Space Agency. Can you tell us a bit more about what Plateau is about and why this mission is interesting compared to TESS and others?
Yeah, I think and Plato, and I hope I get the details right, but from my basic knowledge, it's going to be kind of similar to Kepler in that it's going to stare at a lot of different stars at the same time for a long period of time, like Kepler did. And so it'll find even more planets in addition to what Kepler and K2 and TESS have found. And it should be kind of a nice sanity check to see if their results agree with Kepler's as they should. And hopefully, just keep finding more and more planets that'll do nothing but bolster the statistics we have.
Yeah, the Europeans emphasize the fact that Plateau will basically be able to observe those stars for very long period of time, not 27 days like TESS for most of the stars, but for a very long period of time. So the idea is truly to detect the transits of those Earth-like exoplanets with the instrument. And then there will be Ariel or any other new space telescope that will be able to analyze the atmosphere of those exoplanets. So maybe you can tell us what do we care about analyzing this transiting exoplanet atmosphere? How do we do this?
Yeah, the how is actually fascinating because it's really clever. So you found the planet already, and you've probably found it using the method Kepler did, which is transit. So we wait for it to pass in front of its star. And what you do is you take spectra. So you measure the amount of light you see at a bunch of different wavelengths. And when that planet passes in front of the star, the wavelengths that it absorbs through its atmosphere are going to depend on what the atmosphere is made of. So if you have a lot of water, you may absorb a lot of infrared light, or if you have a lot of carbon dioxide, you may absorb other wavelengths. So we really precisely measure the spectra before and after it transits. And if we see a drop at certain wavelengths when it transits, we can use that to decode what the atmosphere of the planet is made of. And again, that's what has already been done at least a decade ago for big Jupiter-sized planets, and now will in the future be done for Earth-sized planets.
And that will be probably a way for us to detect this presence of biosignatures, which could be indicative of the presence of life, any type of life, in the atmosphere of those exoplanets, on the surface of these exoplanets.
Yeah, if we find a planet that has a large amount of oxygen, for example, we know all the oxygen on Earth came from biological processes. Oxygen is a volatile, combustive element. It's what lets us breathe and move around and have lots of energy. But we know that if it's not continually being replenished, it's going to be used up. So if you see a bunch of oxygen on the planet, that's a good sign there's likely life. If you see even more complex hydrocarbons or something like that, it's another good indication. And if you see something like really complex chemicals that on Earth are only made by humans, if you happen to see that in another world, that may be an indication that there's a civilization on that world. So that would be a really unexpected find, but not outside the realm of possibility.
Thank you, Jeff. So my last questions for you on a personal level, professional personal level. Now the Kepler catalog is released. What's your next big step in your career, or what's your next big project?
We'll see. I don't know. There's a lot to choose from out there, and it's really a flood of exciting projects in astronomy overall, and especially exoplanets. TESS continues to find more and more planets each day. People are still coming through Kepler data to find more planets. I'm working with some folks on that. And I think the real exciting one is the next generation of telescopes. In the US here, there's two proposals or two concept studies that have been done called HABEX and LUVOIR that are both similar in design. And they both want to find, so now that we know, every other sun-like star has a planet probably similar to Earth, they want to actually find those planets. So let's look at the stars within 30 light years. Let's see if we can find those 4 or 5, or go out and find a couple dozen Earth-type planets and actually be able to measure them as well and find out their atmospheres. So if those launch in the next, 1 or 2 decades and get involved with that, that would be really exciting. I think that's for me, that's personally a really exciting next step in this research.
Thank you. Thank you to all our viewers as well for following us. I remind you that the SETI Institute is a non-profit organization. So you can follow us, join us by following our social media, register, clicking on this button here somewhere at the bottom of this YouTube video to get a notification when we post a new video. We talk with scientists using SETI Live about a specific topic. We organize panel conversation as well. This is an outreach that we provide at no cost, so we are grateful for your donations, and that makes this program possible. And thanks again, Jeff, for your time, for telling us the wonder of this discovery. This is not science fiction. Now we know that in our galaxy, there is at least 300 million potentially habitable exoplanets. So that's a great news. Thanks a lot, Jeff, again. Thank you to the team, and thank you for our viewers for watching us. Bye-bye.